Hello, welcome back to our meteorology class. Today we're going to talk about the atmospheric circulation, and this is our sixth topic for this meteorology course. So, for today's content, we're going to tackle the subtopics. First, we're going to discuss the scales of the atmospheric motion, and also we're going to check the local wind system and as well as the global wind circulation and a little bit of what is monsoon, and we're gonna also see the westerlies and define the jet streams. And also we're gonna discuss the La Nina and La Nino southern oscillation. All of this we're gonna learn today. So we're gonna start with the scales of atmospheric motion. The scales of atmospheric motion. uh, Again, when we talk about the atmospheric motion, that means the movement, right? The motion of the air in the atmosphere. So the air in motion is what we commonly call wind. So it might be invisible, but we can see evidence of it nearly everywhere we look. So we can feel it. And in general, motions in the atmosphere actually vary in size from the tiniest wind gust to the wind system that encircle the entire globe. So, for example, the westerlies, we are familiar that the wind actually were defined or were called or were labeled by the name where they are coming from. I mean, they are called westerlies because, for example, this describes the wind that predominantly blows across the mid-latitudes from the west to east. So that means winds are called from the direction that we're blowing from. So, and these scales of atmospheric motion, it simplify the descriptions of the atmospheric circulation by sorting out events according to size and the time frame in which does the wind system occur. So the hierarchy of motion from tiny gusts to giant storms, this is what we call the scales of motion because it simplified the description of the atmospheric circulation. And why is it simplified? Because according to sizes, they are different. For example, for weather maps, the weather maps reveal larger scale wind patterns. So, such as examples, these traveling cyclones and the anticyclones. Also, meteorologists divide winds into these three categories of atmospheric circulation, such as the microscale, the mesoscale, and the macroscale. So keep in mind that motions in the atmosphere vary in the size from the tiniest, from the tiniest wind gust to the wind systems that encircle the globe. That's why it's important to simplify the description according to size and time frame, and that's how meteorologists divide this into three categories. And we're gonna check this one by one. So these are called the scales of motion again. First is the microscale winds. So microscale winds, from the word itself, from the name, it's very obvious that it is the smallest scale of air motion. So aside from their size, these small, often very chaotic wind, they only normally last for only few seconds or at most minutes. So that is about the microscale winds. They are small and only last a few seconds to few minutes. So the next to microscale, this is just mesoscale. So the mesoscale winds generally last for a few minutes to several hours and occasionally last a few days. So this is a middle-sized phenomena, often less than 100 kilometers or 60 miles across, but can be also up to 1,000 kilometers wide. So obviously this is the second to microscale, second to the smallest. This is middle size phenomena. But also you have to bear in mind that not all wind systems fit nearly within one of these categories. Because, for example, the small tornadoes are considered microscale, whereas the large ones, the large tornadoes, are classified as mesoscale winds. So these mesoscale winds, they include strong updrafts and downdrafts tornadoes, as well as the few larger wind systems referred to as local winds, which we're gonna check out in the later slides. So aside from this microscale and mesoscale, we also have this macroscale winds. Of course, this is the biggest among the three. And obviously, this is the largest wind patterns, and it is divided into two categories. First is the planetary scale, and next is the synoptic scale. So for the macroscale winds, first we have again the planetary scale winds. And these planetary scale winds are exemplified by the westerlies and the trade winds. We've mentioned what are the westerlies in the previous slide, and then the trade winds. These are the winds that carried sailing vessels back and forth across the Atlantic during the opening of the New World, respective to the history. So that's why they're called trade winds. And these planetary scale winds are exemplified by the westerlies and the trade winds. So again, this is macro scale wind because this is a large scale flow pattern extend around a large scale flow pattern that extends around the entire globe and can remain essentially unchanged for weeks at a time. So it's unlike the previous wind patterns that we've seen, that it only lasts for a few seconds or a minute or a day. And now this, since this is a large pattern, a large wind scale, so it could remain unchanged for weeks at a time. And the second category for these macro scale winds is what we call the synoptic scale. These synoptic scale is somewhat the smaller macro scale circulation. So this is a little bit smaller for the planetary scale, and this is what we call the weather map scale. So since this is what we call the weather map scale, and there are two well-known synoptic scale systems that are, and these are the traveling mid-latitude cyclones and the anticyclones that appear on the weather maps as areas of low and high pressure, respectively. So low pressure for the cyclones and the high pressure for the anticyclones. We're familiar with this already with the previous topics. So these weather producers are confined largely to the middle latitudes. That's why sometimes they're called the mid-latitude cyclones and the mid-latitude and anticyclones. So those what I've mentioned are the winds that are categorized under the macro scale winds. So to check what I have just mentioned about the three different scales of atmospheric motion, these are the illustrated picture to make it more visible. As what you can see in the first column, we have the wind gusts that is under the smallest scale, which is the microscale. And then next to it is the tornado that's under mesoscale. And the third one is the hurricane, which is obviously under the macroscale. So you can also see in here that the bottom part, the bottommost part are the scales, and upper to it is the time, the seconds to minutes. The lifespan of this wind. For example, the wind gust that is shown here, it lasts from seconds to minutes, and this is the example of microscale, because of that it's just small and it lasts not that long. So another example aside from the wind gusts is the microburst and dust devils. And if you're not familiar what is dust devils, these are common in arid or dry region of the world, and they are whirling vortices, and these are small, well-developed vortices resemble tornadoes. So they are much smaller and less intense than most tornadoes, though. So they are not tornado, but they are called dust devils. And however, in the second picture, these are what we call the tornado under the mesoscale. And for the lifespan, it lasts from minutes to hours, because yeah, this is a little bit bigger than the microscale. And another example of the mesoscale that lasts hours to days are these local winds, and which we're going to talk about in the later slides. So for the mesoscale, again, tornado, these producing supercell thunderstorms exemplify the mesoscale wind system as shown in this illustration or in this picture. And then next to it is the hurricane. What you can see in here is the satellite image of hurricane. So this image of hurricane is an example of macro scale circulation, or the weather map scale. And if you can notice here, again, the macro scale is divided into two different categories. First is the synoptic, or the weather map scale, which is the example here is a hurricane. And the second one is the planetary scale, which that includes the waves in the westerlies, or the trade winds. So these are the three scales of atmospheric motion, or scales of motion in simpler term. Now we're proceeding to the local winds. What are these local winds? Again, we know that these are the examples of these are examples under the mesoscale winds. And mostly these local winds are linked to temperature and pressure differences that result from variations in topography or in local surface conditions. And I've mentioned that winds are named for the direction from which they blow. So this is very true for the local winds. And in this figure, it illustrates the different types of local winds: the sea and land breeze, valley and mountain breeze, Chinook or foreign winds, the Katabatic or fall winds, and the country breeze. So these are the local winds that are named for the direction from which they blow at the surface. For example, a sea breeze blows from the sea toward the land. So that's the local winds. And to check one by one for these examples, first here we have the sea breeze and the land breeze. In this picture, you can see we have in the left side that it shows during daylight hours, the cooler and denser air over the water, which is in this area, is a high pressure, moves these cooler and denser air. This moves into the land, and thereby this is what we call the sea breeze, because this moves into the land and generates sea breeze. So this is the sea breeze, and comparing to the land breeze, it's the opposite. At nighttime, the land cools more rapidly than the sea, and thereby it generates an offshore flow called the land breeze. So the land is more cooler, the high pressure goes to the low pressure. So the land to the water, that's why it's called land breeze. So this pressure difference again causes the air aloft to blow away from the land. So the land is for example, here in the sea breeze picture, in the first picture. So this is the area of high pressure. So the air above, because of the difference of the pressure, this causes the air aloft here to blow away from the land toward the water area. So this water area is the area where there is a low pressure. So the flow above, this flow, the flow aloft, is called the return flow. So even though it generally develops before the sea breeze, this is what we called the return flow. And that then goes on to create the sea breeze. So the surface circulation that develops from this redistribution of mass from the sea toward the land, this is what we call the sea breeze. And the opposite is the land breeze. So again, during the daytime, the daylight, it's the sea breeze. The breeze is it blows from the sea towards the land surface. In the nighttime, it blows from the land towards the sea. And next is what we call these valley breeze and mountain breeze. So a daily wind similar to land and sea breezes occurs also in these mountainous regions, such as this in the picture that is shown in the picture. So during the daytime, the air above the mountain slopes here is heated and it rises, thereby creating a valley breeze. So this valley breeze, this is what we call the valley breeze, because the air is warm and it rises, and then the cool air is sinking here in this valley, and then it rises again as it warms up. So the warmer air glides up the mountain slopes and generates the valley breeze. So valley breezes can often be identified by the cumulus clouds that develop over the adjacent mountain peaks, as what you can see here. These breezes may account for late afternoon thunder showers that occur on warm summer days, because this is during the day, because above the mountain, the air above the mountain slopes is heated and rises, creating a valley breeze. And the opposite to that, during nighttime, as what you can see in the second picture, at night, air above the mountain cools rapidly and drains into the warm valley below, then creating a mountain breeze. So this is the mountain breeze because it comes from the slopes and it blows towards the valley. The cold air is sinking and the warm air is rising. This is what happens after sunset, and this is the reverse pattern of the valley breeze. So the rapid heat loss along the mountain slopes cools the air. Because of the nighttime, there's no solar light anymore. So that happened, and which drains into the valley. So this is what we call the mountain breeze. So similar cool air drainage can occur in hilly regions also with modest slopes. So, and this results to the coldest pockets of air and are usually found in the lowest spots. So that's what we call the mountain breeze. And the cloud development on the mountain peaks that signals the occurrence of a daytime upslope, or the valley breeze, as what you can see in the picture again here. This is the cloud development that could signal the valley breeze. And at the nighttime, the opposite, the shrinking of this mountain bridge towards the valley, is what we call the mountain breeze. So this valley breeze is most common during warm seasons when the solar heating is most intense. It's very visible here at that stand, and this mountain breeze tends to occur more frequently during cold seasons. So this is what you can see as an example of the cloud that developed on the mountain peaks, and this signals the occurrence of the valley breeze, the daytime upslope of the valley breeze. Another example of these local winds is what we call the Chinook. This is termed in the US and Canada, and Fon it is what they call in the European Alps. So this is the warm and dry wind that flows down the leeward side of the mountain slopes. So from in different localities, it's called Chinook, for example, in the US and the Canada, and Phones for the people who are in the Alps. So this wind is going down to the leeward side, or the side that is protected from the wind, and this is very warm and dry. There is what they call the Santa Ana. This is a Chinook-like wind in the southern California and northwestern Mexico that happens during fall and winter. So the Santa Ana is another local name, and again it occurs in the southern California as a hot, dry Santa Ana wind that greatly increased the threat of wildfires. So to be shown here in this picture, in this figure, it shows the wildfires driven by Santa Ana winds. And as what you can see in the small image, there is this satellite image that shows an idealized high pressure area composed of cool, dry air, and this what drives the Santa Ana winds. So the adiabatic heating causes the air temperature to increase and the relative humidity to decrease. That's why these Santa Ana winds are driven towards Los Angeles and San Diego coast, as shown in this picture, in this image. What we call the katabatic, or the fall winds. So these katabatic or fall winds is the winds that travel from ice or snow-covered highlands, driven mainly by the force of gravity. So gravity causes the cold air to cascade over the rim of a highland like a waterfall. So although the air is heated adiabatically, the initial temperature are so low that the wind arrives in the lowlands still colder and denser than the air it displaces. So that's what we call the adiabatic, rather akatabatic or fall winds. And there is what we call the Mistral, which blows from the French Alps towards the Mediterranean Sea, and Bora, for which this kind of wind that originates in the mountains of Balkan Peninsula and blows to the Adriatic Sea. So this is called Mistral again from French Alps, and Bora from the Balkan Peninsula. So this is just illustration. This is just the illustration of this katabatic winds, which is also known as Mistral or Bora, a few of the better known katabatic winds, which have the local names, the Mistral and Bora. This is how it goes from the ice or snow-covered highland. It travels towards, this is mainly driven by the force of gravity. It travels down, and as it cascades over the rim of this highland, it falls, and even if it travels down and heated adiabatically, the initial temperatures are still so low that the wind here, the lowland, are still colder and denser than the air it replaces or it displaces. And last of these local wind examples is the country breeze. These are called country breezes because the circulation patterns is characterized by a light wind blowing into the city from the surrounding countryside. So these one of the mesoscale wind, and these breeze or the country breeze is associated with large urban areas. Why? Because in cities, massive buildings, such as with big rocks, retain the heat accumulated during the day more than the open land of outlying areas within the city. So that's why it results that the warm, less dense air over cities rises, which in turn initiates the country to city flow. So that's why we call that country breezes, because it form this warm, less dense air rises, which in turn initiates the country to city flow. We're going to the global circulation because we've talked about the local winds. Now we're going to check the global circulation. So this global circulation actually came from the knowledge of two sources. So first is the pattern of pressure and winds observed worldwide. So next is the theoretical studies of fluid motion. So these two, the pattern of pressure and winds observed worldwide, since this is global circulation, as well as the theoretical studies of fluid motion, not just wind, is what influences or where the knowledge of global winds came from. So in this topic, we're going to check the class model of global circulation that was developed largely from average worldwide temperature distribution. So from this classical model of global circulation, we will then see the modified or idealized model, which is the more realistic wind patterns using the three-cell circulation model. So we have a model for this global circulation in order for us to visualize what really is the global circulation. So it does not only come from the patterns of pressure and winds, but also from the theoretical studies of the fluid motion. And we're going to check what it really means as it shows in the model. We have the first classical model, but later on we're going to see the more realistic wind patterns, which is modified using the three-cell circulation model, because in this we added the rotation of the earth as one to be considered, while in illustrating this model. So first, as I mentioned, the single cell circulation model. So these came from George Hadley in 1735, because one of the first contributions to the classical model of global circulation came from Hadley, from George Hadley. So this single cell circulation model is a simple convection system produced by an equal heating of the atmosphere on a non-rotating Earth. So we are aware that the solar energy drives wind. So George Hadley proposed that large temperature contrasts between the poles and the equator creates a large convection cell in both the northern and southern hemispheres. So as what you can see, this is a global circulation on a non-rotating Earth. So in this model, in Hadley's model, the warm equatorial air rises. So the warm equatorial air rises, this one, until it reaches the tropopause, where it spreads towards the pole, where cooling causes it to sink and spread out at the surface of the equator ward, moving. So it's just like that. It's going up and then coming back down. So this is in general just the concept of the global circulation of an unrotating Earth. So as these, for example, as this cold polar air approaches the equator, it is reheated again and rises again, and it's the same pattern. It goes back and forth. The air rises and then it goes to the polar, and it is spread, and there's the surface flow, and it's reheated again and goes up again and goes down and goes up, and it's opposite for the southern hemisphere. Although this concept is correct, or I mean this principle is correct, but this model, or this model of Hadley, does not take into account the rotation of the Earth. So this is again the non-rotating Earth. So that's why another model is, that's what we call the three-cell circulation model, is developed. So the three-cell circulation model is imposed in the 1920s that incorporates now the Earth's rotation, unlike Hadley's model. And this time, this three circulation model includes the Hadley cell, the Ferrel cell, and the polar cell. So it is better shown in this illustration, in this picture, the idealized global circulation for the three-cell circulation model on a rotating Earth. You can see that this is the Hadley cell, and this is the Ferrel cell, and this is the polar cell. So we're gonna see this again in the next few slides, because first is the Hadley cell, and this Hadley cell happened in the zones between the equator and roughly 30 degrees latitude north and south, as what you've seen in the previous picture, right? So this Hadley cell is between the equator and roughly 30 degrees latitude north and south. So the circulation closely resembles the convection model proposed by Hadley. That's why it is named as Hadley cell in his honor. So the near the equator, the same concept, that warm rising air releases the latent heat. So And then the air begins to subside in the zone between 20 degrees and 35 degrees. And this a subsidence of the air is because of the radiation cooling. The air becomes denser and it sinks. Because remember that near the equator, the air was warm and it rises and it releases the latent heat, and that's why it later on in the upper part, reaching the 20 degrees and 35 degrees latitude, this is where the zone where the warm rising air begins to subside because of the radiation cooling. The air becomes denser, that's why it sinks. And aside from the radiation cooling, there is also the factor of Coriolis force that restricts the poleward flow of air. So before, this was not accounted, this was not considered in the single cell model. But this is the Hadley cell, which is a very familiar, or it resembles the convection model proposed by Hadley. That's why it's still called the Hadley cells. So remember that the Coriolis force becomes stronger with increasing distance from the equator, if you remember in the previous lecture. So because of this increasing, or the force that becomes stronger with the increasing distance from the equator, the Coriolis force is stronger in the poleward, causing the poleward moving of this upper air to be deflected into the nearly west to east flow by the time it reaches the 30 degrees latitude. So again, that's why one of the reasons why this air subdue, or the air sinks, because of the Coriolis force, that it restricts the poleward flow and it deflects into the west to east flow. So these causes in general a pileup of air, or the convergence aloft, results to the subsidence, results to sinking. And actually the sinking air splits into branches. So first is the equatorward flow, because these two branches is the air that sinks from rising, then it sinks, and then when it sinks, it splits into branches, one flowing poleward and one flowing toward the equator. So the one that flows towards the equator, or what we call the equatorward flow, is deflected by the Coriolis force to form the what we mentioned, or what we called the trade winds. And so the reliable trade winds, so called because they enable, again, they are called trade winds because they enabled early sailing ships to move goods between Europe and North America in the northern hemisphere. So the trades blow from the northeast, while the southern hemisphere, the trades are from the southeast. And these northeast trades converge with the southeast trades along the boundary that is what we call the ITCZ, or the Intertropical Convergence Zone. And this zone is also what we call sometimes doldrums, because in Intertropical Convergence Zone, there is a region near the equator that has a weak pressure gradient, and that's why it's called doldrums. So the trade winds from both hemispheres, from the south and from the north, meet in this zone. In here, that's why it's called doldrums, because there's light winds and humid conditions. So there's a weak pressure gradient, or also what we call the intertropical convergence zone, because these trade winds from the northeast trades, it converged with the southeast trades. So that's it for the first cell, because this is the 3-cell circulation model. This is the first cell we call the Hadley cell, right? If you remember, it incorporates 3 different cells. First is the Hadley. So next to the Hadley cell is the Ferrel cell. And this Ferrel cell the circulation happens between 30 degrees and 60 degrees latitude, north and south, both between the 2 hemispheres, the north and southern hemispheres. And this is proposed by William Ferrel, so that's the name Ferrel cell, to account for the westerly surface winds in the middle latitude. So this is accounting the westerly surface winds in the middle latitudes. So these westerlies, we've mentioned about the westerly surface, westerlies, this Ferrel cell is accounting the westerly surface winds in the middle latitude, because before, it was already known to Benjamin Franklin, an American weather forecaster, that these prevailing westerlies, he noted that storms migrated from west to east across the colonies. So Franklin observed that the westerlies were much more sporadic and therefore less reliable than the trade winds for sail power. And this is also that we need to account for the circulation. And prevailing westerlies is, as defined officially, the dominant west-east motion of the atmosphere that characterizes the regions on the poleward side of the subtropical highs. So again, just in general, this Ferrel cell accounts for the westerly winds, so the westerlies, the prevailing westerlies. And just to define the prevailing westerlies, this is the dominant west to east motion of the atmosphere that characterizes the regions on the poleward side of the subtropical highs. So it's called westerlies because it's blowing from the west. And the third cell is what we call the polar cell. The circulation of the polar cell is driven by subsidence near the poles that produces a surface flow that moves equatorward. So this surface flow that moves equatorward is what we call the polar easterlies in both hemispheres. So and these cold polar winds encounter the warmer westerly flow of the mid-latitudes. That's what we call the polar front. So the region where the flow of cold air clashes with this warm air is named the polar front. It's this polar cell is called polar cell because it happens in the poles, and it's mostly driven by the subsidence of the air near the poles. So to better see this in picture again, what I've been explaining, here is the idealized global circulation for the 3-cell circulation model on a rotating Earth rather. So again, in this is the Hadley cell. It happens the circulation happens both the northern hemisphere and the southern hemisphere. So this is the Hadley cell, and this is the Ferrel cell, and this is the polar cell. It happens in the polar region. So it is labeled here, and this is what we call the polar front, where the the air converges, the warm and the cold air converges, and also in this subtropical highs, this is a region where it's also called the horse latitudes, because for some historic reasons, where the sailors, they happen to get stuck somehow in this area, and then they should throw away horses because they run out of food and water for the horse. So that's why it's called the horse latitude. And in this latitude, this is where the subsidence happen of the Hadley cell, because if you remember that the warm air rises, and up until this horse latitude, or this 30 degrees latitude, it subsides again. So in the air, the arrow subsides again, and where in this area, in their intertropical convergence zone, it's called the intertropical convergence zone because the subsidence of this air circulated, as illustrated in the Hadley cell, meets in this area from the northern and then from the southern. Say they subside here, I mean they converge here, and again also termed as doldrums. So and in the upper air we can see that there is a Ferrel cell, and it's the similar action of the warm air rises. The warm air rises here, and it flows, it goes down again, and the polar cell also the same circulation, and this is just the idealized global circulation for the three-cell circulation model that I have mentioned one by one in the previous slides. And you have to remember that the primary wind zones, including the trade winds, which flow toward the equator. Here is what the trade winds, the northeast trade winds, because it's coming from the north and the east, so it's what we call the northeast trade winds. And the opposite of that is the southeast, because remember it's coming from the east, right? So that's why it's called the trade winds. It's coming from the east, and the westerlies is always coming from the west. West to east, the arrow is coming from the west to east. This is what we call the westerlies, and then the winds that are coming from the east to west, this is what we call the trade winds. And and also remember that the westerlies in the middle latitudes, and the polar easterlies, which flow away from the poles. So this is the polar easterlies. This is the wind that's from the pole and coming also from the east, that flows away from the poles. So these are the primary wind zones of this idealized global circulation, wind circulation. Again, the polar easterlies, the westerlies, and the trade winds. We're heading on to the general circulation and the precipitation patterns. If you want to take a break at this moment, you can take a pause, a 10 to 15-minute break, and then come back for this general circulation and precipitation patterns and the rest of this lecture. For the global precipitation patterns, it is said that the position of the major features of the general circulation and their latitudinal displacement, which annually averages about 10 to 15 degrees latitude, it strongly influenced the climate of many areas. So, for example, as shown in this figure in the globe, as what you can see, the rising and sinking of this air that is illustrated in this left side of the globe, it's associated with the major pressure systems of the Earth's general circulation. So you can see that where the air rises in here, you have to take note that the precipitation tends to be abundant here in these blue regions where the air rises. So compared to where the air sinks, these are the drier region prevails in tan shade. And note that the sinking air of the subtropical highs produces the major deserts regions of the world. And consequently, areas with high rainfall exist in the tropics, where humid air arises in conjunction with the ITCZ, or the Intertropical Convergence Zone, in between 40 degrees to 55 degrees latitude, where middle latitude storms and the polar front force this air upward. And also, the areas of low rainfall are found near 30 degrees latitude in the vicinity of the subtropical highs, 30 degrees here around this area, and in the polar regions where the air is cold and dry. And in general, that's the global precipitation pattern. It is actually determined mainly by the semi-permanent pressure systems, as well as the distribution of land and water and the air temperature, and also with a factor of the terrain or the landmass. So that's how the global precipitation pattern gets affected. And next, we're going to check what is monsoon. So now we're gonna know what is monsoon. We're still talking about the global circulation of the Earth, and in contrary to the popular belief, monsoon actually does not mean rainy season. So monsoon is a large seasonal changes in Earth's global circulation. So this is what we define as monsoon, and it refers to a particular wind system that reverses its direction twice each year. So there is what we call the winter monsoon. This is the winter associated with winds that blow predominantly off the continents. And that's why it's called winter. And for the summer monsoon, this happens during summer. Warm, moisture-laden air blows from the sea towards the land. Usually, this is associated with abundant precipitation over affected land areas. And for monsoons, the Asia's monsoon. And in this Asia's monsoon, this circulation pattern occurs in conjunction with the seasonal shift of the intertropical convergence zone. And what you can see here in this picture is the onset of summer. With the onset of summer, the ITCZ moves northward, and in the arrows moves northward over the continent, and this is normally accompanied by peak rainfall. And actually, the circulation pattern of this Asia's monsoon is strongly influenced by the seasonal change in the solar heating of the vast Asian continent. Therefore, this monsoonal circulation is associated with large seasonal migration of the ITCZ. And in this certain example that is shown in the first figure, this is the summer monsoon, since it's very strongly influenced by the seasonal change because of the solar heating. And during summer, this is like, for example, the onset of summer, the ITCZ, or the Intertropical Convergence Zone, where the air is converging, So this moves upward, northward over the continent, and normally this is accompanied by peak rainfall. And yeah, with the onset of summer, the ITCZ migrates northward and draws warm, moist air onto the continent. And the opposite of this is the winter monsoon. And this opposite occurs in the Asian winter as the ITCZ moves south of the equator. It shows the arrow is moving southward compared when you compare to the winter, to the summer that is moving northward. In the winter, it's moving uh, towards the southern part. And this happens in January, where a strong high pressure develops, and this high pressure develops over in this region in Asia. So this results the flow of the cool air of the continent that generates the dry winter monsoon. So, and that is for the Asia's monsoon circulation. And we have this North American monsoon. What is North American monsoon is just the same monsoon but happened in the North America and has a circulation pattern that produces a dry spring followed by relatively rainy summer. So hot summer temperatures over the southwestern United States, it generally generate the North American monsoon, as what you can see in here, shown in this picture. The high temperatures, it creates a thermal low that draws here the thermal low that draws this moist air from the Gulf of California. It draws this moist air from the Gulf of California and Mexico. So this summer monsoon produces an increase in precipitation, which often comes in the form of thunderstorm. So these happen over the southwestern United States and as well as the northwestern Mexico. And that's what we call the monsoon. Another are the westerlies and jet streams. And up to this point, we have seen that temperature contrast around the globe results in semi-permanent pressure systems, which in turn produce surface winds and earth precipitation regions. So now it's time to know the westerlies and the jet streams. We've mentioned the westerlies. These are generally the wind that are coming from the west, right? And among the most important discoveries of in the history or even from before was that airflow above or airflow aloft in the middle latitude has a strong west to east component. That's why it's strong west to east component moving or flowing from the west towards the east. That's why it's called the westerlies. And this is why we learn that the winds above the middle latitude in both hemispheres, both northern and southern hemispheres, blow in a way west to east direction. So the reason for this westerly winds is that aloft or above, we generally find higher pressure over equatorial region and lower pressures over the polar regions, if you still remember that. And these westerlies are driven mainly by temperature contrast between the poles and equator. So you can recall that if you still remember that because cold air in denser or more compact, right? The cold air is more denser and more compact than warm air. So the air pressure decreases more rapidly in a column of cold air than in a column of warm air. So therefore, the pressure gradient aloft or up above is directed from the equator, which is where we can see the area of higher pressure, towards the poles, where the area of lower pressure. And these westerlies, aside from driven mainly by the temperature, it is also the Coriolis force that redirects poleward moving air to create westerly flows. So this temperature contrast that makes the movement of the air from the equator towards the poleward, and then because of this Coriolis force, it deflects the movement and it redirects the poleward moving air to create the westerly flow. That's why it goes to the west, because of this Coriolis effect. And that's why, because of these factors, again, the westerlies up above or the westerlies aloft do not flow along straight paths. So, but instead, they follow a wavy or meandering paths that have long wavelengths. And these large waves in westerly flow, this is what we called Rossby waves. Or this is the term for these large-scale motions, because it is attributed to Rossby. And who is Rossby? This is the first to explain the nature of these large waves that is discovered. The waves that are deflected through because of the Coriolis force. And to see here, this is the idealized airflow of the westerlies aloft. You can see here is in the bigger, there's a bigger waves. This is what the Rossby wave. And you can also see here the jet stream. So the jet stream actually is the fast core of this wavy flow. It's just where you can see these upper level wind tend to concentrate in narrow bands. We find rivers of fast flowing air. That's what it is termed as jet streams. So this is the cold air. For the jet streams, we're still talking about this fast flowing air that travels. We have two different jet streams, the polar jet stream and the subtropical jet stream that is illustrated here. So first, we're going to check the polar one, and it is said that this polar jet stream is created by large temperature contrasts at surface. So again, the key of this polar jet stream is the large temperature differences at the surface, and it produces steep pressure gradients aloft, and therefore it generates the faster upper air winds because of these steep difference of the temperature. And the position and speed of the polar jet stream actually changes with the seasons, obviously because of the temperature changes. And this polar jet stream is the most prevalent jet stream that occurs along a major frontal zone that is called polar front, because where you can find this large temperature contrast, there there is this long, narrow linear zone that is cold fronts, and one of these major frontal zone is the polar front. This is where the polar jet stream is occurring. So again, the polar jet streams is found in this polar front, and it is mainly created by large temperature contrasts. And aside from this polar jet stream, we have the subtropical jet streams. And this is a cross-sectional view of the polar and subtropical jets in relation to the three-cell model of global circulation. We've seen the three-cell model of global circulation. We have the Hadley cell, the Ferrel cell, and the polar cell. And now this is where the polar jet stream is located. And because you remember, this is the polar front, and then this is where the polar jet stream is located. And below is the subtropical jet, of course. And this subtropical jet stream is a semi-permanent jet that is located about 30 degrees latitude in both hemispheres, the northern hemispheres and the southern hemispheres. That's why it's called subtropical jet stream, because it's in the 30 degrees latitude. So unlike the polar jet, which is generated by marked temperature differences found at higher latitudes, there is no strong temperature contrast in subtropics. And therefore, this subtropical jet stream is mainly the consequence of Earth's rotation. So primarily, the Earth's rotation, the fact that Earth and the atmosphere rotates faster at the equator than places at higher latitudes. So how can we say this, that the Earth, including the atmosphere, rotates faster at the equator than the other places at higher latitudes? Because imagine a parcel of air starting at rest relative to the Earth's surface, let's say, high over the equator. So there's a parcel of air starting at rest high over the equator. And as the air moves poleward as part of the upper Hadley circulation, it conserves its rotational velocity. This is what we call angular momentum. So such that it moves faster than the Earth's surface, because it's closer to the equator, and as it moves poleward, it somehow conserves its rotational velocity. So as a result, the subtropical jet is created as air aloft moves towards the pole, and the Coriolis force turns these accelerating winds to the right until finally, at about 30 degrees latitude, they are moving eastward. So the resulting fast-moving stream of air traveling from west to east is what we know as the subpolar jet stream. And this subpolar jet stream is the wintertime jet that is weaker than the polar jet stream. So again, this is a semi-permanent jet, unlike the polar jet streams that that is marked mainly by, or created mainly by, the temperature differences, the steep temperature differences. The subtropical jet is mainly the consequence of the Earth's rotation, and it is weaker than the polar jet. Now, for the last part of this lecture, we're gonna talk about El Nino, La Nina, and Southern Oscillation and check its definition. I think we're all familiar what is El Nino, right? And in order to better understand the event of El Nino, what really happened during the El Nino, in this illustration, it shows the relationship between normal conditions and the El Nino. In the upper part, this is the normal condition shown in this picture. Under normal conditions, there is this strong trade winds that is shown in these arrows. Strong trade winds that carry this strong equatorial current. These strong trade winds drive the equatorial current towards the west because when we say current, that means that refers to the currents in the ocean. And these strong trade winds, because they're very strong, they drive this current, this ocean current, equatorial current, towards the west. And at the same time, because uh, there is this high pressure area in this in the eastern part, and there is a upwelling that is happening in this area of the west coast of South America. So this is upwelling is when there is an upward movement of the water. So due to the Peru current, Peru is in South America, the Peru current is causing the upwelling of this water, of the cold water along the west coast of South America. And in contrast to that, during an El Nino event, because this was during a current or normal event rather, and an El Nino event, as what you can observe, is the pressure over the eastern Pacific drops. If you can compare in a normal season, in a normal condition, there is a high pressure here in the eastern Pacific. But in El Nino, in an El Nino event, there is a drop of the pressure over here in the eastern Pacific, while the pressure over the western Pacific rises. So this causes the trade winds to diminish. So because of these weak trade winds, it leads to an eastern movement of warm water along the equator. So there is this strong countercurrent. This strengthens the equatorial countercurrent, causing surface waters of the central and eastern Pacific to warm. So in this area now, as it's shown in the red color, it was now warm with far-reaching consequences for weather patterns. As what you can see, it is the opposite in this area, from high pressure in the eastern Pacific. Now it has become a low pressure, and then there is this diminishing or weak trade winds. That's why there is a strong countercurrent towards towards this region of the eastern Pacific that warms the ocean, that warms the water. Actually, this phenomena or this event is first observed by the fishermen in Ecuador and in Peru. Both countries are located in South America. That's why it's called El Nino, actually, because El Nino refers to the boy in English translation. This happens when nearing Christmas or in December. That's why they call it El Nino. We're still here gonna check the sea surface temperature anomaly associated with El Nino and La Nina. So El Nino, you can see the high pressure off of the coast of South America weakens, and this reduces the strength of the trade winds, as I've mentioned, and creates the strong equatorial countercurrent, if you remember the previous picture. So, which amasses large quantities of warmer than normal water along the west coast of South Africa. And that's why there is a temperature anomaly in the sea surface. So the circulation associated with El Nino eventually returns to normal conditions or is replaced by a La Nina event, the opposite of El Nino, because El Nino means the little boy, La Nina means the little girl. So as what you can see in here, there is a difference from El Nino. This is the high temperature in maroon, in dark red, and La Nina is in blue. So this is South America, and this is the Eastern Pacific Current, that where you can see the sea surface temperature anomaly during this El Nino and La Nina event. Because, yeah, again, if El Nino, there is this high pressure in the South American currents, and then thereby reduces the strength or weakens the strength of the trade winds, and then creates a strong equatorial countercurrent. So instead of the current going to the west, now it creates a countercurrent going to the east. So, and it gives the warmer than normal water along the west coast of South America. So this is the South America, and then this is the east coast of South America, and this is the west coast of South America. So it's going to the east, but it's when you locate the South America, this is the west coast of South America. This is happening in the west coast of South America. And the counter event to that, the circulation of El Nino is returned to normal conditions or replaced by La Nina event, which is now shown in this picture. So the El Nino events again bring the warmer than normal sea surface temperatures to the equatorial Pacific off the west coast of South America. And these tends to be associated with wet conditions in coastal South America and drier than normal conditions in Indonesia. So this is in the globe, you can see, or in this picture, you can see that this is the South America. If this brings, if El Nino brings a wet conditions in South America, actually in Indonesia, in the other direction, the opposite, and the opposite, in the opposite side, there is a drier than normal conditions in Indonesia. And again, the event La Nina is the strengthening of normal conditions, and it is the opposite of El Nino, resulting in drier than normal conditions in western South America rather, and it floods the northeastern Australia as well as Indonesia. So it's just the opposite. It's really the opposite. Now for the La Nina, the South America now is drier than normal, and in Indonesia it's flooding, including the northeastern Australia. So the atmospheric circulation in the equatorial Pacific during the La Nina is dominated by stronger than average trade winds. So these wind systems in turn generate a normal, generate a strong equatorial current that flows westward away from South America towards the Indonesia current. And therefore, the circulation pattern is associated um, with low pressure in the Western Pacific and can result in flooding in northeastern Australia and Indonesia, whereas it results in drier than normal conditions that occur along the coastal areas of Western South America. So that's the situation that happens during El Nino and La Nina. The southern oscillation, El Nino and La Nina events are strongly related to changes in the global pressure patterns. So the low pressure in the Western Pacific again strengthens the trade winds, which move warm tropical water toward Australia and Indonesia, right? As I've mentioned. So by contrast to that, in the contrary, a decrease in pressure in the Eastern Pacific weakens the trade winds and strengthens the equatorial countercurrents, which amass a large quantities of warm water along the coast of Peru and Chile. So this is now the El Nino event. So the changes in atmospheric pressure create a wind patterns that produce the weather associated with El Nino and La Nina events. So therefore, these oscillation of pressure systems in the equatorial Pacific oceans that leads to formation of El Nino and La Nina is what we call the southern oscillation. So if these seesaw pattern of atmospheric pressure between the eastern and western Pacific because of these events is what we call the southern oscillation. And together, when you say El Nino and southern oscillation, it's familiarly termed as ENSO, El Nino Southern Oscillation. So those events that were illustrated, the El Nino and La Nina illustrated in pictures that was shown in the previous slides, actually was strongly related to global pressure patterns, right? Because of the high pressure and low pressure, and these strengthens the trade winds and weakens trade winds and so on. So these oscillation or these seesaw pattern, these changes of atmospheric pressure is what we call the oscillation, and it's happening in the south, so it's what we call the southern oscillation. So together it's called El Nino Southern Oscillation or ENSO. And that's it, our lecture for today. And in summary, winds are classified as microscale, the smallest, mesoscale, the intermediate, and macroscale, the largest. So this macroscale is subdivided into planetary and synoptic scale motions. So this is one of the first ideas that we have seen today. And also we have to take note that monsoons are large-scale seasonal changes in global circulation that tend to produce wet summers and dry winters, as well as trade winds exist between the equator and 30 degrees latitude. The circulation between 30 degrees and 60 degrees latitude, both north and south, results in the prevailing westerlies. So the airflow aloft, or the airflow up above in the middle latitudes is predominantly from west to east. That's what we call the westerlies. So the westerlies are driven by the pressure gradient aloft caused by the temperature contrast between the poles and equator. And so the last point is El Nino and La Nina events are part of global circulation and are related to a seesaw pattern of atmospheric pressure between the eastern and western Pacific that is called the Southern Oscillation. So these are the main few points that you have to remember to take note for today. So much and have a nice day.